So far we have derived in our last video the Pauli matrices, that is sigma x, sigma y and sigma z. This is a generalized relation of the derivation of the Pauli sigma matrices from the angular momentum operator J. If I put I equal to x, then from Jx I can construct sigma x, and a similar thing happens for y and z also. Now, as these Pauli matrices are diagonal in nature, as we have just derived, so our mathematical analysis will be much more easier now, because then we need to deal in finite dimension only. Otherwise these matrices are in finite dimension. So these Pauli matrices are very much convenient for us because of their block diagonal nature. Let's discuss the time evolution in quantum mechanics. Time evolution of what? Time evolution of the state. Now, state is extremely important thing in quantum mechanics, because this wave function psi contains all the information related to the system. This wave function is not a physical quantity though, but if we want to measure, suppose position, then we need to find out the expectation value of the x operator in this wave function, in this state psi. So finding psi is extremely important in quantum mechanics, and this is the very important and significant postulate of quantum mechanics, which is the Schroedinger equation, because this equation tells us about how psi changes with time, that is how the system evolves with time. And evolution of the system, that is evolution of this psi with time, is known as quantum dynamics. Now this is Schroedinger equation, and for the time being I am considering this Hamiltonian operator as time independent for our convenience. In position space, the wave function, the component of the wave function in position space is this one. This thing we have discussed in the Dirac notation videos. So in x space, psi will be psi x, which is component of psi in position space. So now before I proceed, let me tell you something, which is, when I am dealing with time evolution in quantum mechanics, that is the quantum mechanics we are discussing, time is taken as parameter where space is taken as operator. That means time and space, they are treated on different footing. Here time is not an operator, it is just a parameter. But when we switch to relativistic quantum mechanics, there time and space are treated on the same footing, and they both are treated as parameter. Space is no longer operated there, but here what we are discussing and what we have discussed so far, time is just a parameter, position is an operator. So now this is my Schroedinger equation in position space, and Hamiltonian is a function of kinetic energy and potential energy. So Hamiltonian is a function of position and this momentum operator, momentum component in x space, but H does not contain time explicitly. We are considering time independent Hamiltonian here. One thing I would like to mention more, that these wave functions are normalized. Initially they were normalized, and as the time evolves they remain normalized. That means their length is not changing. Initially their length was 1, and as time progresses their length does not change. Now, as we are considering time independent Hamiltonian, if we consider time dependent Hamiltonian, then we will write that time independent Hamiltonian as time independent part of the Hamiltonian, plus the time factor will be introduced as a perturbation. Perturbation means some external disturbance kind of thing. We can think about that for the time being. Later we will discuss about perturbations. Suppose a system is if I consider this pen, this is here at a minimum potential energy configuration, that's why it is sitting here. But when I will apply some magnet over here, so the metal portion will be attracted towards the magnet, so that magnetic field will be a perturbation to this pen. Now, what is the advantage of taking the time independent Hamiltonian? Because if we take time independent Hamiltonian, then we can readily solve this Schroedinger equation, and we can construct our psi like this. And from H we can easily measure, we can easily evaluate this exponential term, and this psi 0 is not time dependent, and as it is not time dependent, this is constant in time. So we have a constant part in the wave function which is psi 0, and we have a time dependent part which comes like this exponential, and this is quite easy to evaluate. So this is my time dependent wave function psi, where this is time dependent factor and this is a constant factor. And in this state psi, we need to find out the expectation value of the physical quantity whose time evolution I want. For example, let me consider the expectation value of position. So by definition, the expectation value of position will be like this, where position is treated as an operator here, not a parameter like time. Now we need to find out how expectation value of the position changes with time, which tells me how the particle changes its location over time. At t equal to 0, that is initially the psi was psi 0. Initially I can find out the expectation value of x like this, and some later time t we can find out the expectation value of the position operator like this. Now we need to find out the expectation value of x for some later time. Initially the position or expectation value of the position operator is like this, and at time t the psi is now psi 0 e to the power I h t by h cross. Just keep in mind this, I am using in place of psi t, I am using this expression. So here I have put the expression of psi t, which is this psi t, which is the wave function psi at a later time t, and this is the evolution of psi 0, time evolution of psi 0. So now this expectation value of x looks like this, and how this expectation changes with time is the most interested thing we'll be discussing. In order to do that, I am making time derivative of that expectation value taken in the psi t state. So I am making a derivative of it as I have considered these position operators as time independent, so this ddt will not act on this x, it will act on only this exponential factor, and after the derivative with respect to time, I found this. This is the time derivative of e to the power I h t by h cross, which looks like this. And we must consider that this I h cross by I h by h cross and e to the power I h t by h cross, they commute with each other, as this term is a function of Hamiltonian h and this also is a function of h, so they commute with each other. Similarly, this term also commutes with this term. This term also commutes with this term. So now the time evolution of the expectation value of x will look like this. And this is the algebra I have done, and after some arrangement I have taken this e to the power I h t by h cross, and here also e to the power minus I h t by h cross, and I am left with this term, which is nothing but the commutation relation of the Hamiltonian and the position. I is a constant, h cross is Planck's constant, so I can take this out. I have taken this out, so I am left with this, because e to the power I h t by h cross psi 0 is nothing but psi t. Similarly, e to the power minus I h t by h cross psi 0 is nothing but psi t. So expectation value of the position operator, how it changes with time, will be obtained using equation 2. And similarly, we can find out the change of another physically measurable quantity, another variable, which is the momentum, and we can find out the change of the expectation value of this momentum with respect to time from equation 3 also. So this is quite simpler. We can easily find out the time evolution of these physical quantities, position and momentum, by just finding out the commutation relation and just taking its expectation value. Let's derive this commutation relation, but before going into that, I would like to show you time evolution of some general operator O, which is a function of both position, momentum and time explicitly. So here this operator will have some expression that will contain one position term, one momentum term, and the time factor will be also there. So for that operator, for general operator, the time evolution will look like this. This factor comes because of the explicit dependence of time in this operator O. So this is this equation 4 will give us the time evolution of the operator O, which has an explicit time factor. Now let's, for example, we take the Hamiltonian in one dimension. This is the kinetic energy term, this is the potential energy term. We need to put the potential energy term as the case may be. For example, if it's a free particle, so V is equal to 0, only the kinetic energy term will be there, and the system will have some positive energy because it is not bound now, it is free now. And if we are talking about harmonic oscillator, then this Vx will be half m omega square x square. We have elaborately discussed harmonic oscillators in my harmonic oscillator video series. So this is my one-dimensional Hamiltonian, which does not contain time explicitly, and this is the commutation relation of the Hamiltonian with the position operator x itself, which looks like this. And as this potential term contains explicitly position, so it commutes with the position operator itself, because this operator or any operator will commute with its own function. This is the formal relation what we know, which is, this is familiar to each other. Now we will be using this derivation, this relation. So if AB, that is the commutation relation of AB, is given as I alpha, where alpha is a constant, then what will be the commutation relation of A with B square? So here I have derived the commutation relation of A with B square. The 2 factor comes because of the square term here. Now as we have B square term here and we have X here, so we need this commutation relation to derive this. Now using this commutation relation, I am deriving X P square, which is I H cross 2P. This is just, I have used this relation. So here I have P square twice m, because P square and X, because this twice m is just a constant, so it is completely unordered because of the, it will remain unaffected. So P square X will be just minus IH cross twice P. This is equation 7. I am going to use this here in equation 6. So substitution of the commutation relation of P square and X will give me the commutation relation of the Hamiltonian with X, which is equation 8, and Hx is minus IH cross P by M. Now I will be using equation 8 into equation 4. We get this thing. I am going to put equation 8 here, and I have obtained equation 9, which is the expectation value of X, the time evolution of the expectation value of X, which is the expectation value of P by M. Now M is a mass, so whenever we are deriving the expectation value of the momentum, we need to find out the expectation of momentum only.